A simple experience can often lead to much writing and crying. It can shake up everything we thought we knew about the behavior of matter and light, and even forever change the way you look at the reality of the world on a microscopic scale. Today, we'll explore Young's double-slit experiment, widely regarded as one of the most stunning and perplexing experiments in physics. Once you grasp it, even if you're completely sober, it might hit you like a ton of bricks. This experiment's principle is fairly simple. Imagine that you have a cannon that can shoot out, let's say, tennis balls, frozen cherries, or anything else in large quantities, small enough to pass through two slits open in a wall. And on the other side of those slits, there's another wall which doesn't have any holes in it, and on which you carefully detect and record the impact points. As more and more throws are made, you would gradually see a large area of the final wall become covered with spots, whose distribution is basically controlled by the distance and angle of your cannon and by the dimensions of the openings. Up to that point, nothing extraordinary. Now, imagine doing the same thing, but this time greatly reducing the size of the device and swapping the frozen cherries for subatomic particles. Let's say electrons still propelled with the help of a small cannon. We shoot electrons one by one toward the two slits. Once again, we carefully note on the other side where the electrons have crashed. At first, these particles seem to be spread out just about everywhere. And as we keep collecting data, we start to see areas that are almost untouched by impacts, while others are overloaded. There are alternating regions where the electrons seem to preferentially crash, separated by others where they almost never go. One might think that these dark areas where they have concentrated, and those where they are conspicuously absent, are actually the result of a kind of shadow cast by the two slits. We observe dozens of alternations, attempting to explain the appearance of these patterns. One might also think that the electrons influence each other during their journey, even though we don't really know how. But they end up spreading out like that at the point of impact. Except that, remember, we shot them one after the other. Each time, we wait for the launched electron to hit the other side before sending the next one. Stay put for now, it's fascinating and you'll see why soon. Because the results of this experiment will force us to accept that reality, taken as a whole, is radically different from what we experience in our daily lives. In fact, the appearance of these strange patterns, called interference patterns, can only be interpreted in one single way. Each electron moved and behaved like a wave throughout its entire journey until it was detected as a particle. If that seems normal to you, then you are absolutely not normal. Let's start over. To understand exactly what's happening, let's imagine that each electron we've launched isn't a particle, but rather a wave. Just like waves that spread across water's surface, what would result? Well, that's exactly what we observe on the other side, those interference patterns. Because when a wave passes through two slits at the same time, it splits to create on the other side two smaller waves, which along their path will interfere with each other. In the same way as on the surface of a calm and placid lake, when two waves created by skipping stones and moving in a succession of peaks and troughs meet each other. They can, if the peaks of their waves overlap, add together and thus double the amplitude of the waves. Or, on the contrary, if their crests coincide with the troughs of the other, their elevations can cancel each other out and thus disappear. In short, what we observe is a mesmerizing effect on the opposite wall. These regions where electrons are detected and those where they are absent are, in a way, like shadow puppets of a final wave produced by the mixing of two small waves that formed after passing through the two slits. Except that, once again, it's really important to emphasize this. During this experiment, the electrons are fired one after another. And each time we wait for each one of them to hit the wall on the other side before sending the next one. And yet each electron individually behaved like a wave, okay? A wave passing through two slits split into two smaller waves that added up and cancelled each other out along their path, before crashing into a single spot on the opposite wall. In brief, things will become more complex from now on. If you still have hair, you might lose it. Let me rephrase it to emphasize how truly remarkable the results of this experiment are. As strange as it may seem, each electron literally went through both slits. Each particle that was sent took both possible paths at the same time, exactly like a wave would. And on this wall, with each shot from the cannon. It's not a wave that is recorded along the entire length, but a single, unique impact that is detected. Where the launched electron appeared, where it specifically went and crashed. And it's only with the repetition of impacts that we see these interference patterns emerge. And this is where it gets extremely weird. Okay, it was already seriously weird. It's that if we reject the idea that each electron takes both possible paths at the same time, and if we place a detector right before the slits that's able to identify the passage of a particle. A detector that will therefore allow us to know through which slit each electron has passed. Then, the interference patterns on the other side disappear, and we clearly observe each electron passing through only one of the slits at a time. Reality is completely crazy. In fact, it's as if, by trying to detect the passage of the electrons, we forced the wave that they were to collapse into the state of particles at the moment of measurement. From then on, the detected particles can only pass through one slit, eliminating split waves interfering after the slits and the strange patterns on the final wall. If you think you fully understand, I haven't explained well enough. Here, the presence of a detector somehow forces the wave to localize, the particle to choose which slit to go through, even if we only observe the slit it doesn't go through. So, when an electron goes through the first slit, its behavior on the other side. The areas where it will preferentially hit will depend on whether the second slit is being observed or not. In other words, trying to find out which slit each electron goes through just by observing ends up changing the result of the entire experiment. And so, through this double-slit experiment, we can show that in the world of the infinitely small, things don't behave the same way when we try to observe them. Or not. And that's still particularly strange. I mean, in our everyday world, things exist and behave independently of our observation. The time it takes for an object to fall, for example, is the same whether you're in the room watching it or not. My behavior in this video is the same whether you watch it or not. Or is it? But at the nanometric scale, everything happens as if that's not the case. This experiment and its many variations have been conducted countless times globally, yielding consistent results. Whether we like it or not, we inevitably come to this conclusion. In the world of the infinitely small, things behave depending on the situation, like waves or like particles. Sometimes both occur simultaneously in the same experiment. This is what we call the wave-particle duality principle, which tells us that every quantum object must be considered both as a wave and as a particle. To roughly sum up this crazy experiment, everything happens as if each electron behaves like a wave as long as it isn't measured. But as soon as we pay attention to it, at the moment, we measure it. When the wave encounters a wall, it transforms and collapses into the state of particles. In other words, in the absence of observers and interactions, a subatomic particle. When it moves from one point to another, it does so by taking all possible paths at the same time. But when we try to measure where it is, it suddenly collapses into points. So, this experiment proves that each electron, from the moment it leaves the cannon until it arrives, behaved like a wave. That it traveled the whole way without a precise position, as if it was in several places at once, surfing everywhere at the same time, on a wave of probability of presence that, when passing through the two slits, split up. On the other side, as a set of recombined waves, destroyed or amplified, the electron traveled until it reached the wall, where its presence was detected. Like a measurement forces it to manifest, to collapse into a particle. Having a position, this time very precise, but also forced to appear randomly. In the regions where the wave is most intense, the amplitude of the waves is the strongest. And so, after thousands of measurements, we see these impacts distributed according to a succession of zones where the electrons will preferentially appear and others where their probability of appearing is extremely low. And thus, these strange interference patterns that we keep talking about are formed. From this point on, if you don't feel your brain boiling, it means you're brain dead. This weirdness isn't only observed with electrons, but also with photons, the particles of light. As I was able to see thanks to a team of physicists from the Commissariat à l'Énergie Atomique who were kind enough to show me that by sending a laser through two tiny, closely spaced slits. You also get, a few meters from the source, alternating bright and dark areas, those beautiful interference fringes that are typical when two waves meet. In fact, this strange wave-particle duality has even been demonstrated with things much larger than electrons or photons. Variants of this experiment have even been done with atoms and even entire molecules. In 1999, they managed to make a molecule made up of 60 carbon atoms interfere. And 3 years ago, they managed to do the same with this monster. An amazingly huge molecule. You have to understand that, in this diagram, each letter R stands for a block containing 10 carbon atoms, 4 hydrogen atoms, 17 fluorine atoms, and 1 sulfur atom. This molecule is made up of nearly 2,000 atoms. That's starting to be quite a big baby. And yet, this large molecule was also observed in a similar experiment, passing through 2 slits at the same time, before its imposing 2,000 atom structure eventually crashed beyond the slits on a detector, drawing interference patterns there. So where does it stop? At what scale is the boundary between the macroscopic world in which we live, where objects behave classically, and the microscopic one, strange and sometimes unsettling, the one we've been wading through for quite some time? Why is it that you or I, who are made up of an aggregate of subatomic particles, don't exhibit quantum behaviors? Why is it that if I'm put in a cannon and shot, I don't end up hurt in 2 places at once? I won't go through both at the same time, but I'll probably just have a bad time. Well, it's thought that this is because we live in a world full of matter, where our atoms interact with each other. Bathed in electromagnetic fields, they are constantly forced to choose their state and therefore can't behave that way for long, as we've seen only under extremely controlled conditions. In short, this ingenious double-slit experiment reveals the wave-particle duality, shows the existence of a wave of density, probability of presence, and that at the observed subatomic scale it influences the very state of the object being studied. At this level of reality, it is impossible to study phenomena without deeply disturbing them. And if you come out of this episode like me, with the unpleasant feeling of being a bit groggy after being immersed in a sticky and strange reality, don't worry. In fact, the opposite would be more worrying. As Niels Bohr, a pioneer in studying subatomic reality, said, anyone not shocked by quantum theory hasn't understood it. What Bohr meant by that is not that it's unclear or that we don't understand anything about it. It's been nearly a century now that everything I've talked to you about has been well understood, or at least mathematically modeled. Every day, the existence of our screens, computers, our phones, MRIs, all of that is proof of it. These things wouldn't exist if that weren't the case. At the Commissariat à l'Énergie Atomique, like in many research centers, we develop devices that, in order to work, require us to precisely understand these behaviors of matter that might seem strange to us. And yet, this field of studying nature at the microscopic scale, quantum physics, is not clear. Because what it tells us about matter is crazy and intrinsically a little bit blurry in the sense that it's extremely complicated to visually represent this reality that it gives us access to. Often the results of these experiments take our common sense, what our intuition tells us about the way the world around us behaves, and then it gently sets it down before smashing it with a hammer. This episode was quite significant.